This is the third video podcast for Chapter 5 on human impacts on forest hydrology. What I'd like to present in this quarter is the paleoenvironmental approach to studying the medium to long term, like decades, centuries, possibly even millennial effect of humans on ecohydrology. Okay, so the problem that we face is that if we try to go out and monitor something as we have for the last 50 to 75 years, we have relatively short-term data sets. I mean, at best, we have data sets that go back to 1850, but that's still not good enough to really understand how human impacts have changed relative to natural climatic fluctuations and trends. So we really need to have that longer-term context and better comparability of processes over different spatial timescales. So the approach to do this needs to be some kind of forensics, and in the case of the environment, we think of paleoenvironmental methods. Now, forensics is like the criminal study of what happened in the past, because if you have a crime, that's something that happened, and then we had that TV show, CSI, Crime Scene Investigations, and so they try to go and use evidence to figure out what has happened, and it's really changed how juries function today because there's a really high expectation that we have a lot of evidence before we convict somebody. What's no different in the environmental context? Hydrologists who employ paleoenvironmental reconstruction are trying to look for evidence to see what happened in history during times when we can't actually observe what happened. Some of the questions that we could try to answer include: how much sediment has been eroding from each specific subbasin since human land use began? What's the contribution of each land use practice over time to things that you can see in paleoenvironmental records? And how does human-generated sediment loading compare to background loading for each subbasin? Now, one of the key things here that you could see in this question is you can't necessarily look at water fluxes directly because they happened in the past and we can't see that. But what we can see is the deposits that those water-based processes have left behind and what's inside of those deposits, attributes of those deposits as well that can tell us what those processes must have been like. Two key depositional landforms that record such history are deltas and floodplains, but others just could be lakes and estuaries or possibly even in the coastal zone. Although what you really want is something that is more specific, something that you have a watershed scale hydrological signal, and then that directly affects the depositional zone. And deltas and floodplains are two areas that are good for that. Deltas, as shown in the photo on the left, are areas where sediment is accumulating at the boundary between a river and an estuary or a river and an ocean. Floodplains, as shown in the photo on the right, are peripheral deposits that occur at the edge of a wetted river flowing boundary. And so floodplains are the depositional, aggradational surfaces that sediment is accumulated on next to the active river. What we can do is we can go to one of these depositional sites and use an appropriate technique to collect what we call a sediment core. The idea here is that if you start at the ground surface and you start to dig down, 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 the further down you go, the further back in time you're going. And so when we take a tube and push it down through the ground, we're going back through history and collecting indicators of the past. Here are two technologies that I've used. A geoprobe drilling rig that we have here in our department is really good for floodplains, and then a vibracore is very good for going into wetlands. Typically with these devices, it might only cost about $100 to collect a core itself, but then there's all the labor and involved in that, as well as then the huge amount of effort to process a core, which can be tens of thousands of dollars. So I'm going to show several examples coming from Chesapeake Bay and then one example from here in Northern California to illustrate the kinds of things we can learn about hydrology using using paleoenvironmental studies to see what the impact of deforestation is on the landscape. So Chesapeake Bay is a very large watershed in the eastern United States. It drains 5 states, and it's very important both for birds as well as aquatic and riparian species of terrestrial organisms and aquatic organisms. So it's very important, and of course it's very important to the economy that for human civilization as well. It's the largest estuary in North America, and it's obviously been very well studied. Historically, the watershed was 95 to 100% forest cover, and there was that initial phase of deforestation that really took off when intensive agriculture got underway in the late 1700s. By the time you get to the Civil War, 60% of the watershed was deforested. Then, as we transition from an agricultural-based economy to an industrial-based economy, people moved from rural lands to cities and concentrated. That allowed forests to come back as lands were abandoned, and so now we're at about 60% deforestation. This is a map of Chesapeake Bay, and there are these dots all throughout the main bay, as well as the tributaries like the Potomac River, the Rappahannock, what's this? This is the Bush River, the Gunpowder River, and so on. So you see all those dots. Well, all those dots are locations where my PhD advisor, Professor Grace Brush, and her students, like myself, over the years have collected sediment cores. If you're interested in learning about a really dynamic and highly successful woman scientist, I encourage you to go on the internet and look up Grace Brush and learn about her phenomenal career, because it could really motivate you. So her and her students, including me, were involved in collecting sediment cores throughout Chesapeake Bay to try to see what is the signal of what has happened throughout this whole watershed as it went through the logging period, intensive agriculture, and then industrialization, urbanization. As one example, an early student, Frumer, looked at this one tributary, which you can see is shown this outline, and this is the estuarine area, and then these little lines off on the side are streams that are coming into it. And the hatching in here shows that there is a wetland here and a forest there in 1650. And then here's a map of the same area in 1980, which shows a somewhat expanded forest, but a dramatically expanded wetland. So in 1980, Frumer went there and trenched through here to see what it looked like in this one peripheral tributary coming out into the main tributary, and then made what we call a stratigraphic cross-section of that going from B to B prime as you head out from the land. Underneath here, what you see are these circles, this like dotted, that shows the prehistoric alluvium. Alluvium is sediment, so that was what was there before. We can see that there is, that's the tertiary deposit. The prehistoric alluvium is this small zone here on the top, and then out in front of that was a tidal marsh. So there was a tidal marsh present where you can see the small marsh present there in 1650. Then you can see out in front of that was estuarian mud. On top of that is this massive amount of modern alluvium, essentially the wonderful farm soils of the Chesapeake Bay region that have eroded away and washed into Chesapeake Bay. And then on top of that, we have a new tidal marsh that's shifted farther out into the estuary. And so the marshes that we see today are creations of human civilization as much as anything else, and the ones that were there before have been lost. Here's a photo that illustrates that throughout the lowlands of the coastal plains of the East Coast and down into the estuaries, you can see massive amounts of sediment accumulation and a very abrupt transition where you had the pre-existing surface from the time when European colonization began, and then the massive amount of sediment that has flooded these lands for hundreds of years now. So if we look at the sediment cores taken from Chesapeake Bay, without getting into the details of the methods, we can see here a table that shows the thickness of sediment, centimeters of sediment per year that have been accumulating in Chesapeake Bay, both in the main bay as well as in different areas like upstream in some of the tributaries, middle of the tributaries, and downstream. So these tributaries reflect these large tributaries here like the Potomac, the York, and these other ones, the Patuxent, and so on. And so what you can see is that the pre-European settlement rate was 0.14 centimeters per year. That's 1.4 millimeters per year. After European settlement, with 20% land clearance, it went up to 0.19. And then by the time we got to 40 to 50% land clearance, we had rates of 0.34. So about 3 times higher sedimentation rates compared to before. Knowing that there's some error in this and accumulating the data across all the different cores, we can ask specific hypotheses and run statistical tests to see if these results hold up. So if we look at the test, are the rates of sediment accumulation the same during pre-European and post-European settlement, in either 20% land clearance or 40 to 50% clearance? The p-value here, if this value is less than 0.05, it means we have to reject that hypothesis, and in fact they're different. And so we can reject it for both the 20% level and the 50% amount of clearance. That's all higher than 95% statistical confidence. And you can look at these other things comparing upstream to downstream and so forth. But the bottom line here is that Europeans fundamentally changed the rates of sediment delivery to the ocean. And as we've already seen, as you log, then that allows for more water yield. More water yield also then drives more sediment yield, as well as higher rain splash and other mechanisms, landslides and so forth, that generate sediment. Another way is to look at an individual core. This is a core taken in Jug Bay by Kahn, and I've replotted the results to make them clearer. For 1,000 years prior to European settlement, relatively low rates of sediment accumulation with modest fluctuations. So we had fires, we had Native Americans doing whatever they were doing, we had hurricanes, floods, we had sea level rise. All these things were taking place, and we had relatively modest rates of change. On the other hand, since 1600, we've seen those rates really skyrocket. In particular, since the Civil War, we have very high rates of, in this case of Jug Bay, about 5 millimeters per year. That's notably higher than the rate of sea level rise. And you can also see that each individual hurricane is discernible. This would be an example of a cumulative impact. So hurricanes are a disturbance already. When you put that disturbance on top of the human effect of deforesting the land draining to this area, then you get a disproportionate magnification, so you see these individual spikes, even spikes back in the 1800s. Now let's look at a California case. So I had a graduate student, Jose Constantine, who did his master's degree looking at the Navarro River. And so in the Navarro watershed, there were many mills that were cutting down trees. And we can see here the operation of those mills really beginning around 1850 and then reaching a peak here in the 1950s and early 1960s. So this main graph that you see here shows the overbank deposition rate on the floodplain in grams per square centimeter per year through time from 1200 AD to present. The inset graph shows our depth-time relationship. That's not so important. And what you can see is there are these background levels that are relatively low. There's a spike here that we think is associated with an earthquake. But then there was a main logging that began in the late 1800s, and that created a huge spike of sediment. Eventually, the available sediment starts to decline and new forests come in, so we see a change in the pollen that shows us that the redwoods that were there before get replaced with disturbance species, and eventually then that declines. Then in the early 1900s, there was more logging as well as a forest fire that took place, and we can see a dramatic increase in sedimentation again, followed by an abatement as conditions change, and then now we start to see changes taking place with further development. So all these studies are showing that we can go in and collect sediment cores and actually see these pulses of sediment in response to changes in land use throughout the watershed, especially when you go from like a forested condition to a grassy condition over a significant amount of the watershed. Even as little as 20% is enough to show change. So the summary here for this kind of environmental reconstruction, monitoring is worthwhile for short-term, high-resolution sampling. But if you really want to look over the time scales of human occurrence here in North America, and then if you're talking about Europe or China, you're talking about hundreds to thousands of years of presence. And so you really have to have longer-term methods. And that's where paleoenvironmental reconstruction comes into play. Okay, so that's the end of Chapter 5.